So we start our second exam with section 2.4. So we left off at 2.3 with our first test. 2.4, 2.5, and 2.6 is really going to get into the graphs of equations and functions and properties of those, all right? So 2.4 is all about symmetry. What's it mean for something to be symmetric? Equal on both sides, right? Like, so if your face was symmetric, you would be able to fold it on half of itself and it would fold like perfectly. I read something once where we are not symmetric, and if you actually go and do like a face swap where you put your left side onto your right side, you actually look kind of weird. I'll have to find it because they did that with like Edgar Allan Poe or some. I think that's what they did, and he looks very weird. I'll bring that book and show you what it is. So we're not symmetric, but supposedly those that have symmetric faces are beautiful. Halle Berry being one. And Brad Pitt. Any arguments there? No, I say they're both good looking, right? Okay. So anyway, what we're going to talk about is not symmetry about faces. We're going to talk about symmetries about axes, okay? So the three that we're going to look at is it symmetric about the x-axis? Meaning if you were to fold it about the x-axis, would it fold on top of itself? Is it symmetric about the y-axis? So if you fold it along the y-axis, would it fold on top of itself? And the origin's kind of weird. The origin is if you folded it twice, once with the y and then once with the x, or kind of catty corner, would it fold on itself? So the first one is the test for symmetry for the x-axis, okay? So symmetric about the x-axis. What makes a graph symmetric about the x-axis is if for every point x, y, x negative y is also on the graph, okay? So notice these are not functions, right? They say symmetric about the x-axis. It's just a graph. It's not talking about a function because here every x would have two y's. It would have a positive y value and a negative y value. Let's go ahead and draw a symmetric graph, and then we'll kind of show algebraically how it works, okay? So let's label the first point in the origin. Let's label him 0, 0. All right, and then let's go ahead and label the point 1, 1, and the point 1, negative 1. So I label the point 1, 1, and the point 1, negative 1. Let's go a little further out. I know these points seem kind of random at first, but then I'll tell you at the end. Let's label 4, 2, so go out to 4, 1, 2, 3, 4, and go up 2. So 4, 2, and let's label 4, negative 2, and last but not least, let's go all the way out to 9, and when we go to 9, let's label positive 3 and negative 3. So we'll go to 9 and we'll go up 3, 1, 2, 3, so this will be 9, 3. And then we'll go to 9 and we'll go down to negative 3. 9, negative 3. And if you want to turn it sideways to connect the dots, you can. Guys, it ends up being a parabola on its side, okay?
So this would be symmetrical if you
folded it about the x-axis. Yep. So I kind of wanted to show you graphically, but then over on the right side, we'll show a little bit algebraically, okay? So do you guys agree that if we were to fold it on the x-axis, it would just fold on top of itself? But then also notice all the points that we labeled. Every x value was 1, 2, 4, 9, right? But then the y values range from 1, negative 1, 2, negative 2, 3, negative 3, right? So for every x value, it had a positive y and a negative y. How do we show this algebraically, generically? This graph is actually y squared equals x. It's like the reverse of a parabola, okay? So the whole idea is if you replace y with negative y and you get an equivalent equation from your original, then you know it's symmetric about the x. So what does that mean? N for y, what am I going to replace it with? Negative y. So all I'm doing is testing it algebraically if it's a x-axis. But what do we know about squaring a negative?
You square root it. Wait, you can't. I don't know.
Right. It becomes positive, right? So do you agree that negative y squared is the same thing as y squared equals x? And what do you notice about it compared to the original? It's the same. And that's the whole idea. Read that sentence again. If replacing y with negative y produces an equivalent equation, then the graph is symmetric with respect to the x-axis. So this is us visually proving it, and this is us algebraically proving it.
Wait, would it still be squared?
Yep, because we don't know what y is, correct? And so whatever y is, we want to square it, but we know the negative is going to go away, right? So like if it's 2, 2 squared is 4, but if it's -2, -2 squared is 4. So you keep it all generic, y's and x's and all the squaring the same. Just think about your signs and what the signs do, okay? So the next one I'm going to do, guys, I'm going to do an absolute value equation, okay? So instead of, you could do a parabola again, but I'm trying to like spice it up a little bit. So the absolute value is 0, 0. What's the absolute value of 0? 0. We don't have to do all of them. Let's jump out to like -5. What's the absolute value of -5? Yes, we'll go out 5 to the left. 1, 2, 3, 4, 5. And we're going to go up 5. 1, 2, 3, 4, 5. Graph that. And then we'll go out to the +5. But what's the absolute value of +5? 5, right? So we go 1, 2, 3, 4, 5. And then you go up 5. And same thing with 10 and -10. Don't you agree that the absolute value of -10 is +10? So that's that very far corner. And what's the absolute value of 10? +10. So we could be doing every point, but that's a little unnecessary. So the absolute value function, guys, is just a v. It's basically you chop off 1/2 of a line and flip it over the x-axis and to make a v. So let's see what the equation is. The equation for absolute value is y equals the absolute value of x. That's what we just graphed, okay? In section 2.5, we're going to be more exact about all. We'll learn all of these. I'm just using these right now for examples. Okay, so let's see how we can test this algebraically. If it's, do you guys agree if we folded it about y, it would fold on itself? Okay, so it says, if replacing x with -x produces an equivalent equation, then we know the graph is symmetric about the y, okay? So what we're going to do is we're going to leave y alone, but what are we going to put in place of x? -x. But what do we know about the absolute value of a positive or negative? It will always be, it will be the positive. So that's the same thing as the absolute value of x, correct? Do you guys agree that we have an equivalent equation? So then again, we were able to prove it algebraically as well. And so whatever you're trying to prove, you're replacing the opposite thing, okay? So we were trying to prove x-axis, so what did we replace? The y's. We were trying to prove the y-axis, so what did we replace? The x, okay? So whatever you're trying to prove, whatever symmetry you're trying to prove, you're replacing the opposite variable with a negative. All right, so origin, a perfect example of the origin is called the cubic. So we're going to put 0 in here. 0, 0 is always in all of our little plots, isn't it? Let's graph 1, 1, because when you cube 1, you get 1. But then let's graph the point 2, 8, because when you cube 2, you get 8. I know it's kind of hard to see when I write that. So 2, 8. So that raises up a little bit so you guys can see. Okay. So then let's go the negative direction. What happens when you cube a -1? It stays -1. So we'll cube -1 and get -1. And then what happens when you cube -2? You'll get -8. So -2, -8. I know. So what it is, guys, it's kind of like a snake. I start with the positive side first. So go from your origin and kind of curve up through that first point and curve up through your second point, okay? And then for the second part, we're going to do the same thing, curve downward through your first point and down through your second point. So it's like a little snake. And again, on probably tomorrow, when we cover 2.5, we'll be introduced to all these different functions, all right? So the key thing is when you replace x with -x and y with -y, so we're replacing both with their negative equivalents, then supposedly it has origin symmetry. So the whole idea here is you flip it once, kind of like it'd be roughly over here, right? If you flipped it this way, it'd be over here, but then if you flipped it this way, it would fall on itself. So it's like 2 folds versus 1. All right, so what's this equation? It's y equals x to the third. So we're going to replace both y and x with their negative equivalents. So this is going to be -y equals -x to the third. But what happens when you cube a negative? Does it stay negative or does it go to a positive? Stays negative, okay? So this is the same thing as negative x cubed. But what can I do to both sides to get rid of the negatives? Divide both sides by what? -1. Yep. What happens when you take a negative divided by a negative? You'll get a positive y, and a negative divided by a negative, you'll get a positive x cubed. So again, notice when we replace both the x and the y with their negative equivalents, we got the same. So this is a perfect example of origin symmetry. All right, so I'm going to kind of go back because I kind of skipped it. Up here I said x-axis symmetry if for every x the y's had both, okay? Let's go back to number 2. It has symmetry about the y-axis if the x's had opposites, right? So all the y's match. The y's were +5, the y's were +10, but the x's were flip-flopped. A +5, a -5, a +10, a -10. And then notice the origin. You have origin symmetry if both of them are opposites. So notice on our origin symmetry, we had 1, 1, but then we had -1, -1. And then we had 2, 8, but then we had -2, -8. Okay? So let's go ahead and flip it to page 2. And this is how you guys are going to tell. So not every graph are you able to graph. So like for example, this one here, if you try to put this in your calculator, you couldn't do it because your calculator only does y equal stuff, not y squared stuff. So there's a little graph that's given to you, but you don't need the graph in order to find symmetries. And that's why I try to show you on this front page. So what we're going to do is we're going to test for x by plugging in a negative y and see what happens. We're going to test for y by plugging in a negative x and see what happens. And we're going to test for origin. So leave room for all 3 tests, okay? So we're going to test for x-axis symmetry first. That means put in a negative y. Okay? So that means in this equation, x equals y squared plus 2, wherever I see y, I'm going to put a negative y. So x equals negative y squared plus 2. Okay? We'll never be able to actually do the math because x's and y's are going to stay generic. What we're really focusing, guys, on is the signs, right? So what happens when you square a negative? It becomes positive. So this is the same as x equals y squared plus 2. Do you agree?
Yeah.
How does this equation compare to the original equation? It's the same. So it has, yes, it has x-axis symmetry. But you don't just stop there, because just because something has x-axis symmetry doesn't mean it might potentially have y or origin. You can have more than one. For example, a circle has all 3. Okay? So let's go ahead and do y-axis symmetry. How are we going to test y-axis symmetry algebraically? We're going to plug in a negative x. So remember, whatever symmetry you're testing, you're plugging in a negative of the opposite. So since we're testing y, we're going to plug in a negative x. So in our equation over here, we're going to write negative x equals y squared plus 2. If you wanted to, you could isolate that variable on the left to make it look like the original. So you're like, okay, I really want a positive x there. So in order to get a positive x, I need to divide everything by -1. So you get x equals a negative y squared minus 2. Does that look like the original?
No.
No. So it does not have y-axis symmetry. No y-axis. So I'm going to just do origin right below here. If you have room to the left or whatever, you can. Origin, guys, you're replacing both the x and the y, okay? So we have a negative x and a negative y we're going to replace. So we have negative x equals a negative y quantity squared plus 2. And again, kind of do the math. We can't do anything with the negative x right now, so the negative x will hang out for a second. What happens when you square a negative? It becomes positive. So we have a positive y squared plus 2. And again, if you want to isolate this x just so it looks like the original, we'd have to divide everything by a -1. And when we divide everything by a -1, we're going to get x equals a negative y squared minus 2. Is that the original?
No.
No, so it does not have origin. All right, so this is what I'd be expecting to see on a test. I want you to show me all 3 things worked out, not just yes, no, no, or something like that. You know, like show me that you tested for it. You didn't just put it in your calculator. Calculator's always a nice check, but this guy actually you couldn't graph in your calculator, so he wouldn't even be able to help you. Okay, so let's do the same thing for example 2. We're going to do it for the equation y equals x to the third plus x. So we're going to do the exact same things where we're going to test for x-axis symmetry first. What do you need to do in order to test for x-axis? Plug in what? Negative y. So we have negative y equals x to the third plus x. And again, if you wanted to get that y by itself, just so it looks like your original, you divide by negative 1. But that means you need to divide everything by negative 1.
y equals negative x cubed minus x.
Perfect. So y would equal negative x cubed minus x. Is that your original? Nope, so we have no x-axis symmetry. So we'll make not original. Oh yeah, it's probably like a nice break from what we did. Okay, up here I'm going to go, yep, not original. I'm just going back and writing not the original, just so we make note of why we said no. That's not the original. So I'm just going back up to those to say that's not our original function we started off with, so that's why it didn't have that symmetry, okay? All right, so on the second test here, we're going to try y-axis symmetry. And I already heard Riley say it. We're going to plug in a negative x and see what happens. So you have y equals a negative x to the third plus a negative x like that. Does that look okay so far? So y is going to hang out. But what happens when you cube a negative? What happens to the sign?
It becomes a negative.
Yeah, it stays negative. So we can write it as negative x cubed. And what happens with a plus minus? Who wins? The minus. Notice our y is already isolated like our original, so the y already equals, but does this right-hand side match this right-hand side?
No.
No. So since this is not the original, there's no y-axis symmetry. All right, don't give up. Just because it doesn't have either of those doesn't mean it couldn't potentially have the origin. In this case, it actually does have the origin, okay? So we're going to test for the origin symmetry. I'm just going to put them right down here in the middle. How do we test for the origin symmetry, guys? We replace both the x and the y with the negative. So we're going to go to our original equation way up here. We're going to write negative y equals a negative x to the third plus a negative x. Does that look okay so far? Let the negative y hang out. And then we already talked about what happens when you cube a negative. It stays negative.
And then that is a negative.
That's a negative as well. But we want to get the y to be a positive y. So what do we need to do to everything?
Divide everything by negative.
Divide everything by negative 1. But what happens there, guys? We'll have a positive y, a positive x cubed, and a positive x. So that is the original, so we're going to say yes to origin symmetry. I just want to let you know, sometimes you'll do all 3 and none of them will work. Like a line, guys, if the line's not going through the origin, it doesn't have any kind of symmetry. Sometimes you'll do all 3 and all 3 of them will be yes. That's a circle. A circle has x, y, and origin symmetry. No matter how you fold a circle, it will fall in on itself as long as it's centered at the origin, okay? So, this is all great, but the mathematicians in you, right, there's little hidden mathematicians in you, you should start arguing this whole idea of x-axis symmetry, because what do we know about x-axis symmetry? This is not a function, right? And we like functions because functions are reality. There's things we can plug in, have inputs and outputs and so forth. So all this jazz about x-axis symmetry, y-axis symmetry, origin, it's nice, but we shouldn't really care about x-axis symmetry because that means whatever we graph was not a function. So that's when we get to objective 2, guys, and so this is really important. We kind of ignore x-axis symmetry, all right? And now we're going to just focus on y-axis and origin, and we're going to call it something different. But the math we do behind it's basically the same, okay? So it says an even function, guys, that's going to be y-axis symmetry, FYI, okay? An even function has y-axis symmetry, okay? And how do we find it? It says if the graph of a function is symmetric with respect to the y, we say that a function is even. That is, for every x in the domain, if you plug in negative x, the function stays the same. And notice that's what we were proving up above. When we plugged in negative x, we wanted the function to stay the same. So notice we plugged in negative x, but the functions are the same. Okay, so it's exactly how we did y-axis. You plug in negative x, see what happens. All right, an odd function has origin symmetry. An odd function has origin symmetry, meaning when we plug in negative x, the y value is completely the opposite. So think of all the O's together. Origin, odd, opposite. Origin, odd, opposite. So think opposite is what we want to happen when we plug in that negative x, okay? So we're going to plug in a negative x, and what happens, our function is completely opposite, meaning every sign has to change to the opposite sign, okay? So we'll do an example of each of these. Actually, I have an example of each, even, odd, and neither, okay? So you can see that sometimes it'll happen, sometimes it won't, all right? What's kind of nice, and I know I use the word nice when you guys probably wouldn't use the word nice, but what's nice about testing about even and odd, you do the same thing no matter what. You always plug in negative x, okay? So up here we had to plug in a negative y and a negative x and y. When you test for even, odd, and origin, all you do is plug in negative x and say, okay, how does that compare to my original? If it's completely like my original, it's even. If it's completely opposite of my original, it's odd. If something's changed and something's different, it's neither. So we always just plug in negative x. Always just plug in negative x. So plug in negative x. That's all we're doing when we're testing for even or odd, okay? Even, odd, or neither, just plug in negative x and see what happens. All right, so let's do that on page 3. So we have, notice it's function notation, right? So here we just had to say y equals x equals because we didn't know if they were functions or not. Here we have h of x, f of x, and g of x because they're actually functions, all right? So to test whether it's even, odd, or neither, we're simply going to find what h of negative x is and then compare it to the original. All right? So the first thing is x to the 4th. So what are we going to do? We're going to do negative x to the 4th minus 4 times negative x squared. All right? So right below it, tell me what happens when you raise a negative number to an even power. It becomes positive, right? So that becomes, we don't know what x is, but it's going to be the same thing as x to the 4th, correct? It doesn't matter whether it's positive or negative. And you guys agree that's going to be the same thing that happens back here. We're going to have minus 4, but then a negative squared is still a positive. So that will just be x squared. What do you notice about that function? X to the 4th minus 4x squared. It's exactly h of x. It's the original. Okay? And so whenever it's the same, that is an even function. Remember, think y-axis. When you plug in negative x and nothing changed, it was y-axis symmetry. So all I did was, okay, so you agree that this is the original?
Yeah.
So what was the original labeled? H of x.
So if it was opposite sign,
It'd be
it would be
origin.
origin.
Or origin odd, yep. And if something's changed and something's different, we're going to see example of both of those here in a second. It'd be neither. Yep.
Okay. I thought
So
it was like
if you come back, and I don't know, I can't think of like some catchy thing to help you remember stay the same as even. I don't know, you know what I mean? But opposite is odd is how I remember it. So let's look at this next function, f of x. What we're going to do is we're going to plug in f of negative x and see what happens. Okay, so notice on all of these, we're starting off the same. Plug in negative x, just see what happens at the end. So when we plug in negative x here, we have negative x to the 5th plus negative x to the 3rd. what happens when you take a negative number to an odd power? Does it go to even or does it stay negative?
It stays negative.
It goes negative, right? So negative x to the fifth. And then would you guys agree that that's the same thing with negative x to the third? It's minus x to the third. Do you agree that this is completely opposite of the original?
Yeah, so it'd be odd.
It's odd. So this is how they show it is it's the opposite of f of x, like that. You see that? The opposite of f of x. So this is odd. All right, I got 5 minutes to do this next one before I get cut off, right? All right, so let's look at g of x, guys. Again, what we're going to do is we're going to plug in negative x and see what happens. So g of negative x will be negative x to the third plus a negative x minus 4. So what happens when you take a negative number to an odd power? It stays negative, so we'll have negative x to the third. What happens with a plus minus? He goes minus. So it's looking like it's going to be odd because everything's changing, but what happens when we get to minus 4? Does he change at all? No, he had nothing to do with x, so there's no reason why his sign should change. So notice this is neither, right? It does not match him exactly. It's not completely the opposite. The first two are the opposites, but the negative 4 didn't change. So this is neither. Not original or the opposite. So that's an example of sometimes, guys, you get neither.